Greetings of the day. I am Dr. Onika Parmar and I welcome you all in this course Fundamental of Electronic Engineering. Today we are going to discuss about the VI characteristics, that is the voltage current characteristics of metal oxide semiconductor field effect transistor, that is MOSFET. So, today we are going to discuss about the VI characteristics of MOSFET. So, in this session we are going to explore the behavior of the voltage and current in the MOSFET. So, these are the outline of today's presentation. So, we are going to discuss the current voltage characteristics of N-channel MOSFET followed by the conduction parameters. Then we are going to discuss about the P-channel enhancement mode MOSFET. Then we will discuss the basic transistor operation of P-channel enhancement mode MOSFET. We will discuss about the ideal MOSFET current voltage characteristics for a PMOS device, followed by the summary of the current voltage relationship of the MOSFET. So, let us discuss about the MOSFET characteristics. The transistor characteristics of a MOSFET, that is metal oxide semiconductor field effect transistor, describes its electrical behavior, how it responds to different operating conditions. These characteristics are crucial for understanding and using MOSFET in electronic circuits. Some important MOSFET characteristics include the transfer characteristics. So, the transfer characteristic shows the relationship between the input voltage and the output current. Here, the input voltage is gate to source voltage and the output current is drain current. It helps in determining the MOSFET's operating region, such as cutoff region, saturation and the active region. Whenever we draw the transfer characteristics represents the relation between the input parameter, that is the input voltage, and the output parameter, that is the output current. So, here the output parameter is ID, that is drain current, and the input parameter is gate voltage, that is gate to source voltage, or we also call it as VGS. So, the transfer characteristics shows the relation between VGS and ID. Here VGS will be in the x axis and ID will be in the y axis. Further, we are going to discuss about the saturation region. So, in saturation region, the MOSFET is fully turned on and it conducts current between drain and source terminal effectively. The drain current remains relatively constant and is controlled by the gate to source voltage and the load connected to the MOSFET. So, in the saturation region, we see that transistor is turned on completely and the drain current remains constant in the saturation region. You will find that there will be no variation in the drain current at the saturation region. Further, we are going to discuss about the cutoff region. So, in the cutoff region, the MOSFET is turned off and no current flows between drain to source voltage or drain to source terminal. It occurs when VGS is below the threshold voltage. So, if my gate voltage is less than the threshold voltage, then the transistor will be turned off and no current will flow in the circuit. So, this region is called the cutoff region. In practical cases, it is not necessarily that no current will flow. Some current may flow. This current is known as sub-threshold current. When the transistor is turned off and there is a leakage current present, that is the sub-threshold current, or the gate has not reached to the threshold voltage and there is a small current present in the circuits, that is the sub-threshold current. So, in the cutoff region theoretically no current flows in the circuit and the device is in the turned off condition. Further, we are going to discuss about the active region. This is the region between the cutoff and the saturation, when the MOSFET partially conducts current on the base of the gate to source voltage. It is the region when the MOSFET are typically used for amplification and switching. Basically, active region has more practical applications in the case of switching. So, this region is the region between the cutoff and the saturation region and it is controlled by the gate to source voltage. Here this region has major application in case of switches. Further, we are going to discuss about the threshold voltage as well. So, this is the gate to source voltage at which the MOSFET begins to turn on. It is a critical parameter for determining the MOSFET's behavior. Threshold voltage plays a significant role in the MOSFET characteristics. It has very important role to play. So, the threshold voltage decides whether the MOSFET is turned on or off. So, minimum voltage required at the gate terminal to turn on the device is known as threshold voltage. Transconductance. Transconductance is again an important term. It represents the change in drain current for a given change in gate to source voltage. It is a measure of the MOSFET's amplification capacity. Transconductance is a very important parameter in case of metal oxide semiconductor field effect transistor. It is the rate of change of the output current to the input voltage. Here our output current is the drain current and the input voltage is gate to source voltage. So, it shows the variation in the output with respect to the variation in input. So, the transconductance is the rate of change of drain current with the change in gate to source voltage. Let us discuss about the output characteristics. The output characteristics shows the relationship between drain current and drain to source voltage for different value of gate voltage. They help in understanding how the MOSFET behaves under varying load conditions. If I say output characteristics, it means that I am talking about the output current and the output voltage. As I have told you, the current remains in the y axis and the voltage remains in the x axis. So, if I say about the output characteristics of any device, I am talking about the output current at the output voltage. Here in the case of MOSFET, our output current is the drain current and our output voltage is drain to source voltage. So, in the y axis there will be ID and in the x axis there will be VDS. So, the variation in the ID with respect to the output voltage shows our output characteristics. One of the very significant term in case of MOSFET is the on resistance. It is a measure of the resistance when the MOSFET is in saturation region. Lower R on value indicates better performance of the device and it shows that if the R on is less, then the power dissipation of the device will be less. So, basically R on is measured at the saturation region, and if we have lower value of R on, then we can say our device is a better device. One of the very significant term is breakdown voltage. It is represented as VDS max. It is the maximum drain to source voltage that the MOSFET can handle without breaking down. It is essential to avoid exceeding this voltage to prevent the damage. If we move ahead of the breakdown voltage, then the device undergoes avalanche breakdown and we can find a permanent damage in the device. So, breakdown voltage plays a significant role in the voltage handling capacity of the device. So, it is the maximum drain to source voltage that we can apply to the MOSFET, so that MOSFET can handle that voltage. If we exceed beyond that voltage, the device may undergo a permanent breakdown or a permanent damage. So, we must not exceed this breakdown voltage. These breakdown voltage are generally represented in the data sheet of the MOSFET. Now, there is term called the gate capacitance. It is represented as C. Normally, capacitance is represented as C. So, there are three capacitance: ISS, CISS, COSS, CRSS. We will discuss about them in the coming lectures. So, these capacitance represents the capacitive behavior of the MOSFET and affects its high frequency response in switching application. MOSFETs play a major role in the case of switches. They have major application in the case of switches. So, the gate capacitance or the capacitance CISS, COSS and CRSS plays a significant role when we discuss about the switching capacity of the device. As the MOSFETs have major role to play in the switching industries, so these capacitance play a significant role in the device performance of the MOSFET. So, let us discuss about the current voltage characteristics of a N-channel MOSFET. As the applied gate to source voltage changes, the ID versus VDS curve changes. The initial slope of ID versus VDS increases as VGS increases, as we have discussed in the previous lectures. So, when we apply gate to source voltage to the device, the drain current increases in the current voltage characteristics, that is ID versus VDS characteristics. Initially, the drain current versus the drain to source voltage curve, the drain current increases initially with the gate voltage. Also, in the equation, VD saturation is equals to VGS minus the threshold voltage, shows that the VDS saturation, that is the saturation voltage of the drain terminal, is a function of the gate voltage. Therefore, we can generate the family of curve for this N-channel enhancement mode MOSFET as shown in figure 1. So, this figure shows the ID versus VDS curve for a N-channel enhancement mode MOSFET. Here ID is in the y axis and VDS is in the x axis, and here we can see there is a family of curve. There are various patterns in a single curve, that is for the different value of the gate voltage. So, whenever we draw the ID versus VDS curve, so VGS will remain constant in those cases, and if we make ID versus VGS curve, then VDS will remain constant. So, right now we are discussing about the output characteristics, that is the ID versus the VDS curve. Here the gate voltage will remain constant. So, we can see that for different constant gate voltage we can get different curve, and initially our ID is increasing when the gate voltage is increasing, that is when the gate voltage is low, ID is also low, that is drain current is also low, and as the VGS increases, drain current also increases. So, we can see there is a family of curve. Here the curve is divided into three regions, that is the active region, the saturation region and the cutoff region. So, when our device is in total cutoff region, that is no gate voltage is applied to the circuit. So, in that case the device goes in the cutoff region and no current flows in the circuit. Now, we have started applying some voltage to the gate terminal. Now, that what happens, the drain current starts to increase. Now we have applied the gate voltage with the threshold voltage. So our device is turned on. Now we increase the value of the drain to source voltage. So as we increase the drain to source voltage, initially our curve moves in a linear fashion, and that is the active region of the device. Now we are still increasing our VDS value. Now the value of the drain to source voltage has fallen equal to VGS minus VTH, that is the saturation voltage. Now the saturation voltage is achieved. As the saturation voltage is achieved, now the drain current will not increase and it will go in a linear fashion. Here we can see our drain current was increasing linearly, and then at the point where the saturation voltage is achieved, the drain current goes in a linear fashion. As the value of saturation is achieved, the drain current goes to a straight line. There is no variation in the drain current. So initially our drain current increases linearly, then it saturates and it gives no variation is found in the drain current. So at the saturation region, the drain current shows a straight line in the characteristics, while in the active region it increases in a linear fashion, and in the cutoff condition no current flows in the circuit. So the curve is divided into three regions: saturation, active and cutoff. The region for which the drain to source voltage is less than drain to source voltage for the saturation value or VDS saturation is known as the non-saturation or the triode region. The ideal current voltage characteristics for this region are described by the equation ID is equals to Kn 2 VGS minus VTN. VTN we can say it as a threshold voltage into VDS minus VDS whole square. So this equation describes the current, that is the drain current, for the triode region. Here we can see the ID is dependent upon the gate to source voltage, threshold voltage and the drain to source voltage as well. In the saturation region, the ideal current voltage characteristics of VGS greater than threshold voltage is described in the equation. Here the drain current ID is equals to Kn VGS minus VTH square or VGS minus threshold voltage square. Here we can see in the equation the drain to source voltage is not present in the equation. That is, even though we increase the value of drain to source voltage, the current will remain in a straight line manner, or it will not be affected by the drain to source voltage, and we can find it in the equation as well. Here in the equation we can see there is no term for VDS, while the ID is dependent upon the saturation voltage, that is VGS minus VTH whole square or VGS minus VTN whole square. We generally represent threshold voltage as VTN or VTH, we can use any of the two terms. So in the saturation region we can see ID is equals to Kn VGS minus VTN whole square. It is independent upon to the drain to source voltage. In the saturation region, since the ideal drain current is independent of drain to source voltage, the incremental or a small signal resistance is infinite. We see that R naught is equals to change in VDS upon change in ID. So this is equals to a infinite value. The parameter Kn, this is called the conduction parameter. The conduction parameter of a n-channel device is given as Kn is equals to W mu n Cox by L, or we generally write it as half mu n Cox W by L. Here we can see W, mu n, Cox and L. So, W is the width of the transistor, L is the length of the transistor, mu n is the current mobility and Cox is the oxide capacitance. So, width, length, mobility and the oxide capacitance, these all are material dependent parameters. They all will vary with the variation in the material. So, if I change the material from silicon to germanium, the capacitance value and the mobility will vary. If I change the width of the transistor, my ID will vary. If I change the length of the transistor, my ID will vary. So, here we can see that the Kn is whole soul dependent upon the material and the geometry of the device. So, this parameter Kn is equals to mu n Cox W by L, these all are highly dependent upon the material of the device. Therefore, in the latest research, we are searching about the high conductivity material, we are working for high mobility materials. So, we are moving from silicon to various other semiconductors also. So, this is the reason. Why? Because the current is highly dependent on the material of the device and the geometry. Here Cox is the oxide capacitance per unit area. The oxide capacitance is given as the epsilon oxide upon the thickness of the oxide. Epsilon is the permittivity of the material. Again Cox is a material dependent parameter and it is dependent upon the geometry of the device. If we vary the thickness of the oxide, the capacitance will vary, where Tox is the oxide thickness and epsilon ox is the oxide permittivity. The parameter mu n is the mobility of the electron in the inversion layer, the channel width W and the channel length L of the metal oxide semiconductor field effect transistor structure. As given equation indicates, the conduction parameter is a function of both electrical and geometrical parameters. The oxide capacitance and carrier mobility are essential constant for a given fabrication technology. However, the geometry or width to length ratio are variable in design of the MOSFET that is used to produce specific current voltage characteristics in the MOSFET circuit. If we change the W by L ratio of the device, the current voltage characteristics will vary. We can rewrite the conduction parameter in the form Kn is equals to Kn dash W by L by 2, where Kn dash is mu n Cox and it is called as the process conduction parameter. Kn dash is process conduction parameter. Normally, Kn dash is considered to be a constant for a given fabrication technology. So, above equation indicates that the width to length ratio W by L is the transistor design variable. The current capability of the transistor can be increased by increasing the conduction parameter. For a given fabrication technology, Kn is adjusted by varying the transistor width. Biasing a transistor in either the saturation or the non-saturation region depends on both gate to source voltage and drain to source voltage. Now, let us discuss about the p-channel enhancement mode MOSFET. The complementary device for a n-channel enhancement mode MOSFET is a p-channel enhancement mode MOSFET. Figure 2 shows a simplified cross section for the p-channel enhancement mode MOSFET. The substrate is now n-type and the source and drain are p-type. The channel length, channel width and the oxide thickness parameter definitions are same those for the NMOS device. Here we can see the cross section for a p-channel enhancement mode MOSFET, and we can see the body is of n-type and the source and drain terminal are of p-type now. So, let us discuss about the basic transistor operation of a p-channel enhancement mode MOSFET. The operation of a p-channel device is same as the n-channel device, except the hole is the charge carrier rather than the electron. A negative gate bias is required to induce an invasion layer of holes in the channel region directly under the oxide interface. The threshold voltage for a p-channel device is denoted as VTP. Since the threshold voltage is defined as the gate to source voltage required to induce the inversion layer, then VTP is less than 0 for a p-channel enhancement mode device. Once the inversion layer has been created, the p-type source region is the source of the charge carrier, so that holes flow from the source to the drain. A negative drain voltage is therefore required to induce an electric field in the channel, forcing the holes to move from the source to the drain. The conventional current direction for the PMOS transistor is into the source and out to the drain. The conventional current direction and the voltage polarity of a PMOS device are reversed as compared to the NMOS device. The ideal MOSFET current voltage characteristics for a PMOS device. Here in the ideal current voltage characteristics of the p channel enhancement mode device are essentially same as the current voltage characteristics of a n channel MOSFET as shown in figure 3. The only difference is that the drain current is out of the drain voltage and VDS is replaced by VSD. So, this shows the current voltage characteristics for a p channel MOSFET. Again here the drain current is in the y axis and the drain voltage is in the x axis. The saturation point is given by VSG saturation, that is equals to VSG plus VTP. For the p channel device biased in a non-saturation region, the current is given by ID is equals to Kp 2 VSG plus VTP into VSD minus VSD square. In the saturation region, the current is given as ID is equals to Kp VSG plus VTP square. The drain terminal, the parameter Kp is the conduction parameter of a p channel device. For a p channel MOSFET biased in the saturation region, we have VSD greater than VSD saturation, that is equals to VSG plus VTP. Summary of the IV relationship of the MOSFET. For a n channel enhancement MOSFET, a positive gate to source voltage greater than the threshold voltage VTN must be applied to induce the electron inversion layer. For VGS greater than VTP, the device is turned on. For a p channel device, all voltage polarities and the current directions are reversed as compared to the NMOS device. For p channel enhancement mode transistor, VTP is less than 0. So, let us do a numerical for this. To calculate the current in an n channel MOSFET, consider a n channel enhancement mode MOSFET with the following parameters: Vt is equals to 0.4 volts, W is equals to 2 micrometer, L is equals to 0.8 micrometer, mu is equals to 650 centimeter square per volt second, oxide thickness is equals to 200 angstrom, and the permittivity is given as 3.9 into 8.85 into 10 to the power of minus 14 farad per coulomb. We have to determine the current of the transistor biased in the saturation for a VDS is equals to 0.8 volts and VDS is equals to 1.6 volts. Here we have to find the drain current. So, the solution for this is here given. Now, Kn is equals to W into mu upon 2L upon Tox. So, if we place the values for W, mu, L and Tox that is present in the numerical, we will get the value for Kn, and if we get the value of Kn, we can determine the current for different value of gate voltage. So, ID is equals to Kn into Vgs minus Vtn whole square. Now, we need to determine the drain current for 0.8 volts and for 1.6 volts. So, for 0.8 volts, if we place the value of Kn, Vgs and Vtn and we place it in the equation ID equals to Kn Vgs minus Vtn whole square, we will get ID is equals to 0.224 milliampere, and for 1.6 volt we get the value 2.02 milliampere. Thank you for attending this session. I hope you enjoyed the lecture. See you in the next lecture.